explore different assumptions to be able to make consistent causal conclusions. And so a typical causal inference problem is typically described by a signature that involves a query you want to estimate, the data you get to observe, and a set of plausible assumptions that are domain-specific and that you typically get from an expert or your own understanding of the domain to carve out a little bit, a smaller subset of models to make your conclusions. And so you can think of the signature of the problem as being passed to a causal inference engine that is supposed to automatically tell you whether your query is uniquely computable. If it is uniquely computable, what would be an expression or an estimator to compute it from finite samples? And even if it's not computable, is it possible to get a tighter bound? And maybe that can still serve as some informative conclusions that will help you in your decision making. And so a lot of the causal inference literature is interested in developing these causal inference engines and proving their soundness and completeness to automatically give you answers for any problem that follows this kind of signature.
Alexis, I think there's a question about clarifying a little bit the notation and the graphical representation of the model P, like the M and the P inside. Okay. I think it's over slide.
Thanks. Yeah, by moving the screen, I don't see the questions in the chat. So thanks for letting me know. So maybe on this slide to start with, when I have a P subscript X, I mean the probability distribution in a model in which we have fixed the variable X to take value little x. So these are interventional probabilities, if you like. The probabilities that don't involve any subscripts, they're meant to be observational. Those are co-occurrences between events that you get to observe by passively observing the system when everything is caused in the normal or natural way without any modification. And so I typically use this notation with the X subscript, but you often see a do notation as well, or the M explicitly written to further specify the model in which you're supposed to take these probabilities. So hopefully that's clear. And so what's really happening in all of these different attempts to do causal inference and these different assumptions is that people are coming up with assumptions that constrain the space of models in different ways. And hopefully under these constraints, try to deduce what would be likely values of the causal effects. Under some constraints, the value of causal effects is uniquely identified. So all the models that are in a given set collapse to one single point, as in the case in this red diagram. And in others, like in the green or the blue one, your assumptions aren't sufficient to uniquely constrain your causal effects, and you're typically left with a set or an interval of different possible values. There is an interesting observation, though, is that most often causal effects are never completely underdetermined. So as soon as you do observe some data, this data allows you to infer some bound on the causal effects. And you know, if this is the only plausible assumptions that you want to make, then that sometimes does give you some information that does allow you to go on with your decision making. Right. So let me give you an example of how you go about making this deduction with in one case in which I give you a causal diagram, I give you the data you observe, and we try to estimate this causal effect. So this particular example is a successful one in which you are able to uniquely compute the value of your query. So first, let me write down a little bit what the graph tells you about the observational distribution. So first, when the graph induces a certain factorization over your observational distribution. So you can follow the edges in the arrow to write the probability of one variable, a condition on other variables, and so forth. This, in this case, is just total probability. And what's happening when you intervene in your system, in this particular case, is that you're replacing the mechanism for your intervention with a fixed value. So under the interventional regime, you go from the probability of x given z to a fixed value of x that you've set. This is pretty much the definition of what it means to have an interventional distribution over, in this case, y and z. And here it's not too difficult to see that if you take this joint distribution on the interventional regime and you marginalize over z, you get the causal effect of x and y. And it's interesting, so you have, so there are several things to unpack here. So first of all, this joint distribution under intervention is one of the first foundational results in the causal inference literature that basically tells you that if you're given a causal diagram without any unobserved confounding, I'll mention something about unobserved confounding later, you're always able to predict the effect of interventions, right? By following this truncated factorization of the joint distribution. That is, by doing exactly what we did before. You take the joint distribution and you replace those conditional probabilities that are that you're intervening on. And so you're left with this updated equation, if you like, that expresses the joint distribution under intervention. Okay. So given a causal diagram and no unobserved confounding, you can always predict the effect of interventions if you have observational data. Now, in our example, we were able to define a particular formula for our causal effect in terms of our observed distribution, right, P. And this is one that you'll probably see very often because it's a very common so-called adjustment or backdoor adjustment formula in which we are reweighting some conditional probabilities with this probability of z. And this is, if you like, a particular expression to compute your causal effects that is maybe simpler to this long list of product of conditional probabilities that we had before. And it basically tells you that if you have a causal diagram with no unobserved confounder, you can always evaluate the effect of an intervention on some outcome y, let's say, by reweighting with the variables that are not affected by x in your causal diagram, also called the non-descendants. Now, in practice, you have a little bit more sophisticated graphical criteria to derive these kind of adjustments formulas. But in general terms, this holds whenever your variables z are non-descendants of your intervention nodes x. And so now and by the way, this kind of adjustment formulas can also be derived under different set of assumptions that don't involve causal diagrams. So in the economics literature, you often find, instead of causal diagrams, assumptions expressed as independence relations between different counterfactual variables. And under a particular common one, which is called conditional exogeneity, that is a very often used, you end up with the same kind of formula for the computation of causal effects. So now I want to say, so now we've seen, I guess, two or various different techniques for various different formulas, if you like, for computing causal effects. And it leads to an interesting distinction between identification on the one hand and estimation on the other hand. So identification just relates identification just asks for one expression that uniquely gives you the value of a causal effect. So something like this one, right? This is an expression in terms of your observational data that will evaluate to the causal effect of interest. But at this point, we're not making any specific recommendation on how you should go about estimating these different terms with data. So how you actually go and compute, estimate these different probabilities, sum over them, and so forth to come up with an efficient way of computing causal effect with finite data samples. And that line of research falls under the estimation bucket. And so I'll just give you now two different examples, two different formulas, if you like, for estimation of the causal effect. On the one hand, you can frame this causal effect as a regression estimator that involves, on the one hand, predicting the value of y given x and given x your treatment and given your covariates from observational data. And then you take your predictions and you average them according to the probability of your covariates. So this is one estimator that you may develop to actually go and compute your causal effect of interest. But you can also use a different one. For instance, another common one is a so-called probability weighted estimator, in which instead of building regression models, you consider estimating a ratio of different probabilities, also called the inverse, let's say an inverse probability weight in this case, where the process is a little bit different. And what you do is you average your observed outcomes y according to this estimated ratio. And the process also involves two steps. You first build a model for the probability of your treatment given your covariates, and you use that as a weight when you take a weighted average of your outcome given these estimated probabilities. And even though in the infinite sample limit, both of these estimators converge to the true causal effect, in finite samples, they may have a very different performance. On the one hand, the regression estimator, the quality of its estimate relies on how well you're able to do this regression. And on the other hand, the quality of the probability-weighted estimator depends on how well you're able to estimate this inverse probability weight. And following up on these two estimators, there's many more techniques that combine these two to create estimators that would be more efficient than any one of these separately. But it's a little bit of a different line of research, more statistics focused, if you like, and finite sampled concerned, in contrast to the infinite sample arguments that people care about in the identification space. So I'll skip over this not identifiable example to and maybe come back to it later to give you a little bit of a sense of how general this approach to causal inference is to tackle a range of different problems in also adjacent fields like transfer learning, reinforcement learning, and try to address some of these robustness questions, decision-making questions that I mentioned in the introduction. Let me do that. So I guess, so coming back to this picture, this signature of the causal inference task, the first thing to note that over the last 2 decades, we've, as a field, developed a range of very sophisticated programs that will automatically tell you the identifiability of any query given a data distribution and an arbitrary causal diagram. So maybe you've heard of a set of rules such as a do calculus or an explicit algorithm such as the ID algorithm. So these are all proven sound and complete. That is, for any query that is identifiable given a data distribution and assumption in theory, these algorithms and these methods will provably give you the correct answer. And from these answers that are maybe complex expressions of your observational data, just as we saw before, we also now have flexible estimators that would repackage these expressions and give you an estimator that will be efficient in finite samples. And even for those that aren't, even for those queries that aren't identifiable, given your data distribution and assumption, there are now very sophisticated techniques also to give you tight bounds whenever possible. So in a sense, this causal inference task, let's say from a very logical perspective and from these very well-articulated assumptions, is being close to being a solved problem, in a sense that we have provably good techniques that for a lot of the different combinations of data distribution and assumptions and queries that you may be interested in. But now I want to argue for perhaps a wider research program that involves the application of these kind of causal inference mindset to more general problems in artificial intelligence and medicine. Because although traditionally we've had quite a narrow focus on the kind of queries that we're interested in reasoning about, it's very much feasible to replace causal effects with other quantities that you may care about, such as counterfactuals or loss terms in different domains, robustness guarantees in domain generalization. If you care about problems of policy evaluation or estimation, you could generalize these fixed interventions to policies that are more general probabilistic or conditional assignments of variables rather than this atomic fixed ones that we've talked about so far. You may also extend these quantities to be really any functional of these interventional probabilities and care about, for instance, notions of regret or reward on the different policies that are common in reinforcement learning. You can think about dynamic treatment regimes in which the actions or policies are sequential over multiple steps. So all of these are possible queries that you can fit into this picture and think about causal inference techniques that would allow you to automatically give you solutions to those. You may also go much further in the type of evidence, the type of data that you have available. So we've talked so far about observational data, but it's feasible in many studies to have a combination of observational data and interventional data. You may have data from randomized controlled trials, perhaps conducted in one domain, and have additional data in your target domain that is of an observational nature, however, and want to fuse those different data sources to compute maybe causal effects in a target domain. So all of these extensions are feasible and can be incorporated into this picture as well. And although there's a lot you can do with causal diagrams, it isn't the only, let's say, inductive bias that you can introduce to your problem to reason about causal questions, right? So instead of having a well-defined causal diagram, you could choose to operate on the output of a causal discovery algorithm, for instance, that typically won't give you a unique causal diagram, but may give you an equivalence class of a causal diagram or a set of those. And you could then be interested in trying to understand the implications of that set of causal diagrams to how much does that kind of information tell you about your query when you combine it with your data. And in problems of a domain generalization or transfer learning, right, instead of having a unique causal diagram, you can imagine that you have multiple causal diagrams, one causal diagram for each domain, let's say, in which you might be able to specify what are the commonalities and the discrepancies between two domains, right? So for instance, you might care about the effect of a drug in in your local population, but only have access to a randomized control trial that was conducted in a different location, where, however, you know that maybe the distribution of some of the variables varies, but importantly, the distribution of some other variables is meant to be invariant. Maybe because those mechanisms relate to some more to say a common causal relationship that is meant to be invariant. So these kind of assumptions you can explicitly feed into these causal diagrams, and then reason about what are possible values of my causal effects under these kind of assumptions. So we've gone actually much further into different analysis with this kind of picture. So to make some of these things a little bit more concrete, I wanted to give you a few examples that I could come up with that that I recognize as causal questions that could be relevant from a medical standpoint. For instance, we talked a lot about the effective interventions in a given subpopulation, for instance, which is an example of the first question, right? A treatment given to patients with stage 3 cancer, for instance. But you may also wonder about the fraction of healthcare expenditures that can be attributed to respiratory illness, for instance. Or yourself, you may be wondering about what would have been the outcome had you conducted a different intervention in the past, right? These questions have more of a counterfactual feel to them. And you could also wonder about questions of discrimination, of harm and benefit, right? For instance, in the case of hospital admission statistics, right? You may wonder whether there's systematic discrimination against a given minority group. All of these questions can be formalized as different versions of this causal inference task. And I mean, going into details into all of them would be a lot of work. There's a lot of literature, but there are existing solutions to deal with each one of these cases. So a few concluding remarks, just to kind of summarize a little bit the things I went over, and maybe the overall message that I want to convey, insights and learnings from taking this model-based approach to data science. Is first realize that if you acknowledge that a lot of the interesting questions that you care about are of this causal or counterfactual nature, the first thing to realize is that a lot of them are provably difficult to answer from data, right? Provably in the sense that they're theoretically underdetermined, no matter how much data you get to observe. And so in my mind, a reasonable approach would be to try to shift most of our effort from data modeling strategies to thinking about good plausible assumptions that are plausible for your problem at hand. Because if you're able to make these assumptions and agree on a set of well-defined, well-articulated assumptions, there's a lot of these questions that you can nevertheless answer, that you can provably answer, right? And often maybe we're too focused on modeling, choosing a specific prediction model for your problem, and you think less about the underlying structure of your data. And that's important because depending on the structure of your system that you assume, the kind of estimation targets will be very different. You'll get very different expressions for the causal effects or the counterfactuals. And if you get that first step wrong, well, you may have very efficient tools, very sophisticated tools, but that don't ultimately answer the question you care about. And so really there's I think over the last century, there's been these two paradigms for data science, and a little bit of a tension, I guess, between data-driven approaches that want to avoid making any assumptions and want their conclusions to be as general as possible, versus other more model-based approaches, where causality really falls into. So yeah, I guess if you care about questions of understanding that go beyond purely predictive questions, beyond really creating summaries of the data you have observed and saying something beyond your data, it's important to take a model-based approach. And finally, also just keep in mind that if you start working with language models and more systems that take many more modalities of data, a little bit like humans, right? So a lot of this logical approach to causal inference is not outdated, but it's a little bit limited because it doesn't it doesn't go beyond reasoning about numerical data, if you like, in some sense. Now, I very much hope that there's going to be a lot of overlap between the logical approach and the more human-centered approaches to causal inference. But it's kind of interesting to see how all these insights can be supplemented with a more human-based approach with all these new techniques that are being explored in the machine learning and artificial intelligence space. Right. So I think that's all the time I have. Thank you very much for your attention.
Thank you so much, Alexis, for this super insightful introduction to causal inference. And I think it was very great to hear your proper intuition on what's going on in like sort of introduction between different paradigms. We have a couple of questions from the audience, and I think they're mostly related to sort of challenging a little bit the causal assumptions that you were mentioning. And so let me start with the first question from Lin Gan, which is, how do you handle situations where the assumptions don't fully hold, especially with complex healthcare data?
Yeah, I mean that's the whole challenge of science, I would say, and it's difficult. We don't have we of course you wouldn't get any guarantees if your assumptions don't match the problem you're studying. So I think your best bet is to roll back a little bit those assumptions. Try to work so instead of operating on one causal diagram, operate on many different causal diagrams and see the kind of conclusions you get from those. So here, I think it's worth mentioning techniques like sensitivity analysis, bounding, but also realize that you do need some assumptions to make causal conclusions in general. So thinking about the assumptions more carefully would be valuable.
Yeah, and I think a very related question, and also sort of getting there into the essence of causality, is would you ever know if sort of something is wrong? So would you ever know if your assumptions that you've made are actually not holding at all? And do you have any guarantees after you have made your analysis and identified your treatment effect according to your assumptions, that like how do you verify that that estimate that you have obtained is actually worth anything?
So in a way, for treatment effects and causal effects, you're in a good situation because these quantities are in principle empirically observable, right? So if you actually were to make an experiment and fix the values of your treatment in the way that you desire, the kind of outcomes that you see from these kind of experiments is your ground truth in a way. So ultimate verification for causal effects will always be a randomized controlled trial of some sort, and comparing the conclusions of that randomized controlled trial with your predictions that you did beforehand.
Yep, great. At least we have one sort of form of ultimate verification. I think that's pretty good news. Does anybody else have any questions to Alexis about causal inference or anything related? Okay, then maybe let me just, oh, yes. What's your view on the plausibility of the unfaithfulness assumption in causal discovery?
Yeah. So the faithfulness assumption relates, I guess, the independencies in data with an explicit separation in the causal diagram. The causal diagram that is the underlying model that generated the data. And it's a little bit tricky because in theory, you can have an independence between two variables, but still have a causal relationship between them. Right? You get these situations, so they're actually quite prevalent in self-regulating mechanisms, where two different paths of interaction between two nodes cancel each other. So it looks like they're independent, but in reality, there's a causal association. Now, the reason why you need or at least why a faithfulness assumption is desirable in causal discovery, is that if you didn't have this assumption, a complete graph, completely connected graph, where every two variables are connected, is always going to be a valid explanation for the independencies that you see in data. In a way, a fully complete model is always able to generate your data if you don't assume faithfulness. And that's fine. It may be that, the world is this way, fully complete in this sense, but it's not a very informative explanation, right? So really, you get the insights from the separations rather than from the connections in causal discovery, which is why people like faithfulness.
So does this mean that if one didn't want to assume faithfulness and that they could do a constraint-based causal discovery algorithm and get a Markov equivalence class or whatever, would that class is kind of like the minimal graph you could produce? Like, if you don't want to say, I know it's faithful, you can say this is like the smallest graph that still sort of, yeah, that could be plausible.
Yeah, I think that's a very nice interpretation. So if you're willing to say that simpler graphs are those with less connections than something like a constraint-based causal discovery algorithm would give you the simplest causal diagram, that is the one with the fewest connections, and still be compatible with the data.
Thanks.
Great. If there is no further questions, maybe just a very open-ended question to you, Alexis. What personally do you feel more like most interested in causality to explore further? Any particular area or any particular problem?
Yeah. Thanks. Indeed, so it's something I have really not talked about at all today. But one of the things I'm most excited about is using causality to understand the alignment of large capable AI systems, right? Because as these systems are incredible, and in many ways they behave like humans in the way they generate data and the way they answer questions, and it's very easy to anthropomorphize their behavior and assign counterfactual beliefs, assign goals, assign values, and all of these notions to me are counterfactual or causal in some way. And at the present time, all of these notions are very vague. They're intuitions that humans have, but we don't have a good way of defining what is a goal, what is alignment in the first place, what are these subjective things that AI systems are meant to have or not. And so what I'm trying to do at the moment is first redefine all of this in terms of a counterfactual query or in terms of a causal query, and then understand to what extent we can predict these counterfactuals, these alignment notions from just observing the agent behaving, right? Can we guarantee that the agent won't discriminate? Can we guarantee that the agent, won't secretly, try to seek power and overcome humans? I mean, it sounds a little bit out there, but in a not so distant future, these kind of questions will come up again, I'm sure.
What do you mean alignment? Do you mean alignment with our human values or alignment between different systems?
I would say at the moment it's mostly alignment with human values, which, I mean, it's kind of warrants, right? Because is there such a thing as a set of consistent human values? But anyway, it goes a little bit in that direction, yeah.
Yeah, great. Thank you very much for this insight. Super fascinating. And thank you so much for the talk. I think on that note, we can finish.
Yes. Thank you so much, Alexis. Thank you very much, Juliana, for presenting both Alex and all the other speakers you have been very kindly presenting this week. And that was a very good and exciting talk, Alexis. Thank you so much. And now we will all take just a 5-minute break, so you can all grab a cup of tea or do what you have to do. And then we will be back here with our large set of exhibition talks of our participants. So be back here in 5 minutes, so 5 after the hour. And then we will start with that.